Today we'll be talking a little bit about chromatography, and we're going to focus more on the theoretical side and how those separations of the mixtures actually occur. So some previous knowledge that I assume you have is just knowing what chromatography is. So just knowing that it's a separation of mixtures. And I also expect you to be able to interpret a chromatic spectrum and being able to calculate the rate of elution, and then having just a basic understanding of what the HPLC is, and also knowing what the Henderson-Hasselbalch equation is and the relationship between the weak acid and the conjugate base. This video is for students who are in upper division chemistry classes, such as analytical chemistry, and so these are concepts that you should have been exposed to previously. If not, just go ahead and review these concepts and then you can continue on with the rest of the video. So just to make sure you have a solid understanding of the concepts I just stated, I put together this quiz that you can take just to have some reassurance. And so go ahead and pause the video and the answers will be on the next slide. Alright, so here are the answers to the self-quiz, and if you did not get these answers, I would just go back through your textbook and quickly review chromatic spectrums and how to use the Henderson-Hasselbalch equation, and then you can continue on with the rest of the video. So now we're just going to do a quick overview of how the HPLC works as an instrument. And so here is where you will put your solvent, which will be your mobile phase, and it will be pumped through the tube, through the column, and through the detector. But before we get to the column, there is an ejector valve, and here is where you actually inject your sample that you want to separate. And so both the solvent and the sample will go through the column at the same time, and this is where the actual separation of the mixture occurs. And so just recall that the more theoretical plates that you have in the column, the better your separation is going to turn out. And so as the individual compounds elute off of the column, they will go through the detector, which has a photomultiplier tube. And just remember that the photomultiplier tube is used for small signals, and it works by having one photon bounce off of a plate, and each time it hits a plate, the electrons double, which make the signal measurable. And so once the signal is recorded, you will see it pop up on your computer screen, and then the solvent and the sample are ejected into the waste. So the column is what we will be focusing on, just because this is where the actual separation occurs, and so we'll kind of get into the theoretical side as to what affects the separation of these compounds. Now let's just take a look at the inside of the column. And on the inside of the column, the stationary phase is bonded to it. And the stationary phase interacts with the solvent and the sample that you want to separate as it passes through the column. And so this has something to do with the separation of those mixtures, which we'll get to a little bit later. Right now, let's just discuss the different types of stationary phases. So the first one is a wall-coated open tubular column, which consists of a liquid stationary phase. The second one is a support-coated open tubular column, which has a liquid stationary phase coated on a solid support attached to the inside of the column. And then the last one is a porous layer open tubular column, which just has a solid stationary phase. And so the support-coated open tubular columns can handle larger samples than the wall-coated open tubular columns. And so why do you think that is? Think about the physical space of the column and the solvent and sample passing through and what's happening. So just go ahead and pause the video for a second and take a couple seconds to think about why this is. Okay, so the reason why support-coated open tubular columns can handle larger samples than the wall-coated open tubular columns is because it has a much higher surface area. And so this allows a lot more interaction between the sample and the stationary phase compared to the wall-coated open tubular column, which just has a flat surface on the inside of the column. Specifically in HPLC, the column is usually made out of pure microporous particles of silica, and the reason this is because it's very permeable to solvent and has a very large surface area. One of the cons of this is that it can't be used above pH 8 because then the silica will start to dissolve in the base. And the structure of silica really plays a role in how the separation occurs, which depends on both polarity and pH, and we will get to that in just a moment. Like I said earlier, bare silica can only be used up to a pH of 8, and that's because it'll start to dissolve in the base. And so if you are working with a solution or a solvent that needs to be at a higher pH, you can use silica with ethylene bridges, which can resist hydrolysis up to pH 12. Now let's talk about the mobile phase. The mobile phase is a solvent that moves through the column and carries the sample that you're trying to separate through the column as well. And it can either be a liquid or a gas in chromatography, but specifically in HPLC, the solvent is going to be a liquid. And so the solvent usually is a combination of water and an organic solvent like acetonitrile or methanol. And a combination is used in order to have the ability to adjust the ratio of water to the organic solvent so that you can manipulate the pH and polarity. Alright, so now we're going to talk about polarity. The order in which the solute components elute off of the column really depends on the polarity of the solvent and the polarity of the compound. And so now we're going to focus on normal phase chromatography, and if you recall, that consists of a polar stationary phase and a nonpolar mobile phase. And so looking at this figure, you can see that the solvent interacts with the nonpolar stationary phase as it flows past it. So remember, when it comes to polarity, like polarities attract. So a nonpolar solute will interact more with the nonpolar mobile phase than the nonpolar stationary phase. And so in normal phase, a less polar solute will elute faster than a more polar solute because it will interact with the stationary phase less and thus move through the column faster. Okay, so let's take a closer look at this diagram. So remember that we're working in normal phase chromatography, which means a polar stationary phase and a non-polar solvent. So we can see that the solvent is flowing in this direction. And as it's flowing, you can see that solute particles are coming off of the stationary phase and starting to interact with the solvent or the mobile phase. And so what that means is that the sample that we're working with here is more non-polar than polar, because remember that like polarities interact. And so if we had a sample that was polar, then we wouldn't see these triangles here interacting with the solvent. Instead, they would still be here on the stationary phase interacting with it because it doesn't want to interact with the nonpolar mobile phase. So now that we've talked a little bit about polarity, it's time for a practice problem. Based on polarity, which solute would elute off the column first in normal phase chromatography? So remember that normal phase means that the stationary phase is polar and the mobile phase is nonpolar. And just think about the polarity of each one to answer this question. You can go ahead and pause the video and the answer will be on the next slide. The answer you should have gotten is benzene. And the reason this is because benzene is only made out of carbons and hydrogens, and so there isn't much difference in polarity between any of the bonds because they're all the same atoms. Now looking at acetic acid, we see that there is an alcohol group and an oxygen double bonded to the central atom. And these oxygens really pull the electrons away from the central carbon, and so that really makes this molecule a lot more polar compared to benzene. Now moving on from polarity, pH is another factor that affects the order of elution. Inside the column, the stationary phase has silicon-oxygen bonds, and it can form hydrogen bonds with the solute, causing a longer elution time. If the solute or sample doesn't contain atoms to hydrogen bond with, or if the solute is deprotonated, then it will not interact with the stationary phase as much, causing a faster elution time. Alright, so now it's time to put those analytical skills to the test. So listed here, I have some statements that have to do with weak acids and conjugate bases in relation to pH and pKa of the solvent and solute. And so as you can see, there are some blank spaces where I want you to fill in the missing word. And so just pause the video and take your time and read through them carefully, and the answers will be on the next slide. Okay, so let's take a look at the answers now. And we'll just go through it point by point. So for the first one, according to the Henderson-Hasselbalch equation, the concentration of the weak acid equals the concentration of the conjugate base when the pH equals the pKa. And this should be nothing new if you have previously worked with the Henderson-Hasselbalch equation before. And so for the next one, if the pH of the solvent is greater than the pKa of the solute, then there will be more conjugate bases than acids present. Therefore, more conjugate base means less interaction with the stationary phase. Now, this should make sense because if the pH of the solvent is greater than the pKa of the solute, then the solute is going to be more deprotonated than protonated, and so therefore it's going to have more conjugate bases present. And so if there's more conjugate base present, it means that it doesn't have that hydrogen to interact with the silicon-oxygen bonds of the stationary phase, and it's going to elute off the column faster. Okay, and so for the last one, if the pH of the solvent is less than the pKa of the solute, then there will be more weak acids than conjugate bases present. Therefore, more weak acid means more interaction with the stationary phase. And this should also make sense because if the pH of the solvent is less than the pKa of the solute, then that means that the solute is going to be mostly protonated and in the weak acid form. And so if there's going to be more weak acids, it means that it has that hydrogen available to interact with the silicon-oxygen bonds in the stationary phase. And so since it's going to be interacting more with the stationary phase, it's going to elute off the column slower. Now that we have talked a little bit about pH, it's time for another practice problem. So, which solute will elute off the column first in normal phase chromatography if the pH of the mobile phase is 5? And so just think about the pKa's of both. So sodium benzoate has a pKa of 4.2 and phenol has a pKa of 10. And so just think about whether it's going to be deprotonated or protonated and how it's going to interact with either the mobile phase or the stationary phase. The answer you should have gotten is sodium benzoate, and this is because since the pKa is less than the pH of the mobile phase, this indicates that there's more conjugate base present than weak acid, which means there's less interaction with the stationary phase, and so it's going to elute off the column first. Now if we look at phenol, it has a pKa above the pH of the mobile phase, so there's going to be more weak acid form than conjugate base, indicating more interaction with the stationary phase as compared to sodium benzoate. So this exercise concludes this video for chromatography, and I hope it was of use. There will be an exercise attached to the end of this video that you could do for more practice, and an answer key will be attached as well. Good luck to you and the rest of your journey in analytical chemistry.